In this video, we're going to solve a momentum collision problem using two different methods that can be applied in several different cases with momentum problems. So first of all, if you're reading a word problem, it's always beneficial to draw as much as you can, especially everything before and after the collision, with some arrows, with some vectors, so that you can make sure you catch all of your negatives. So here is the beginning of my picture, and I'm going to label stuff for before the collision and after the collision. And it's not important to spend a lot of time with the actual drawing, but just making sure everything is labeled properly. So a question would read something like this. We have two kids that are running towards each other, and one of the kids is 70 kilograms, and the other one is 85. So I guess they're actually pretty big. And for the after, we still have the same people, so 70 kilograms and 85 kilograms as well. Now they're both running towards each other, one with a velocity of 3 meters per second, the other one of 2 meters per second. So here's the part where you have to make sure you draw in some stuff so you catch some negative signs. So we have this person going to the right at 3 meters per second, and this person going towards them at 2. So one thing you want to make sure you identify is which direction you call negative. So I just call everything to the right positive and anything pointing to the left negative. Therefore, I'm going to drop a negative sign in this way. Now, if they use a general term like towards, then that means this 85 kilogram person could be going to the right, and then this 70 kilogram person could be going to the left, which would change their directions and the sign of their velocity. But in the end, you're going to get the same answer. It's just going to be a different sign based on how you identify positive or negative. Okay, now afterwards, we want to know what happens to the 70 kilogram person if the 85 kilogram person gets knocked backwards at 2.5 meters per second. Okay, now you can't go off of the words that you read in the problem because backwards would usually cause people to put a negative sign in front of their velocity. But if this person was already going in the negative direction, if they are sent backwards, that's to the right, so that's actually the positive direction. So we're going to go ahead and use the conservation of momentum, which is the sum of all the momenta of the system before and after the collision is equal. So P is momentum, that equals mass times velocity. So all you have to really do is write down all of those M's and V's on the left and then set them equal to all M's and V's on the right. So that's exactly what we're going to do. All right, so all I did is I took my picture and I always draw it horizontally. I don't stack the before and after pictures on top of each other so that I can just take my numbers and slide them directly down, which has proved to be a very effective method in keeping my numbers organized. So I took my mass, my velocity, dropped them down. Same thing with all the rest of them. And then I found the product of each of the M and V's besides this one because the VF is unknown. So I had 210 minus 170, so I have a total of 40 kilogram meters per second on this side. My 85 times 2.5 is 212.5, so I subtracted that from both sides, which left me with a negative momentum of 172.5 on this side, equal to that 70 VF. Finished off by dividing both sides by 70, and I got a velocity of negative 2.46, which means that this person does get sent backwards in this direction at negative 2.46 meters per second, and then that is my final answer. So that's a method that I usually use when I'm doing a collision problem. But there's a second method that proves to be just as effective, and it also might be more beneficial in other cases depending on what variables you're given. So let me go ahead and clear the screen, and we'll go ahead and set up the second method. All right, now for our second method, we are going to use impulse. So impulse has two formulas, and impulse can also be written as J as well as delta P. I like delta P because delta means change in, and then P means momentum, and impulse is change in momentum, so it just makes it clear for me and people who are looking at the variable as well. So we can do momentum, or excuse me, impulse is force times the time of impact, or mass times delta V being V final minus V initial. Okay, so impulse is the change in momentum. And earlier we said that the total momentum of the system doesn't change. So now what we're going to do is take a look at the impulse for each of the people. So we'll call this person A, and we'll call this person B. Okay, so we'll basically say the impulse of person A is equal to the negative impulse of person B. Now they're going to be opposite signs because in these different cases of conservation of momentum, if one thing gains momentum, that means the other one is losing momentum. So it's always going to be opposite signs of one another. So let's go ahead and expand that out into this blue formula over here. Now we don't have forces and times. I was just showing you that that is one of the formulas that can be used in certain cases, but just not for this case. So I'm going to go ahead and cross that out so we don't focus on that one. And let's go ahead and use this impulse formula for each of our um, students or kids that are running towards each other and see what we get for the final velocity. So now using our second method, we just focused on person A, who is 70 kilograms. Their final velocity is unknown minus their initial velocity of positive 3. I took this negative, dropped it straight down. We have an 85 kilogram person. Their final velocity is 2.5, subtracting their initial velocity of negative 2. So it's basically adding 2.5 and 2 together because we're subtracting a negative. And then we get this fairly large negative momentum. We added 2 tens to both sides and then divided by 70, which all should look pretty similar. And it gave us a final velocity of negative 2.46 meters per second. Okay, so this is really just preference on however you want to view the problem. Like I said, my personal preference is the first method, but the second one is just as effective and it has you focus on one person at a time, so that can be helpful for some people. But also, depending on what variables you're given, certain methods might be a little bit more effective or intuitive than the other one. So I hope that was helpful in helping you understand a collision problem using these two different methods. Thank you for watching and listening.